Well, thank you all for coming, and well, thank you to the organizers for the invitation. It's really been an honor being here, and so far it's been excellent. I love it. And I've been going to be talking about ongoing research. I don't have closed results, but I have a lot of insights, I think. And I want to motivate. I think these are exciting times for MIP and for LP. Finally, there is something happening in linear programming, which in my opinion is quite astonishing. It's been around for a while. And so let's go into it. So this is joint work with Roberto Comenetti and a lot of input from good friends, David Applegate, Marcos Golcolea, Daniel Duque, Eduardo Moreno, Juan Pablo Vielma, and Dan Binstock. So what I'm going to be doing is, well, I'll try to convince that we do need other LP algorithms. I'm going to show you how what we have fails miserably when we really want to push the boundaries of what we solve. I'm going to talk a little bit about alternative methods, and I'm going to show some theoretical results on things that should work in theory. And then I'm going to show you how it goes in practice. And there is, of course, a gap, but quite a bit of opportunities in my opinion. So let's go. Why another LP method? And the common wisdom in our community is that LPs are easy. And you can solve large LPs consistently. You can use warm start, and that's why we can actually solve MIPs. I mean, if we were trying to solve MIPs using integral points, we won't be anywhere near what we get today. And moreover, we always think that MIPs are hard because of the MIP side, not because of the LP side. And there is good evidence that this holds for many, many problems. This is MIP-lib, MIP-lib 1, 3, 2010, 2017. It's 1,200 plus instances. These are computational results for all of the LP relaxations of those problems using Gurobi with barrier, simplex dual, simplex primal. This is time, logarithmic time going there, and in this axis, number of non-zeros. And there is no clear winner, but we are able to solve fairly big problems. I mean, if you look here, we are talking tens of millions and probably a couple of hundred of millions LPs in, well, not too bad. I mean, 3 hours. There are a few timeouts, but I mean, that's fair. Why not? And if you look number of iterations, well, simplex, either primal or dual, you have this kind of very nice linear shape going up. But if you look at barrier is quite surprising. I mean, it's very consistent. If you go over 200 iterations, it usually means that something is wrong. You are not doing it right, or there is something else going on. And that's quite surprising. Of course, not everything is solved. This machine is 32 gigs of RAM. There are 3 hours of time limit. Actually, barrier fails more essentially because it's hungry in memory. So there are quite a number of large instances where the memory it's just too much for the constraints of the machine. But even then, primal dual simplex also die sometimes for other reasons. But the truth is that this is kind of a chicken and an egg problem. We solve problems that we can solve, and if we cannot solve it, if you could talk to an engineer, what they will do, it will simplify the problem so that they can solve it. But there are problems that are much bigger than those. So think about large pricing problem for airlines. You are looking for at least one variable for every flight for some number of periods, and you are also looking at all origin destinations in kind of aggregated historical. Those are big. Resource constraint, project scheduling problems, and when I say that, I'm actually thinking in mining problems, which is quite big in Chile, and that's how we started working on those. And you also have the so-called joint network design and scheduling problem. What's that? Think about any of the big ocean shippers, Myers, whichever, and think, how do you decide how to place your ships to publish your routes so that you maximize the amount of shipping goods that you can take from anywhere to anywhere, taking into account that you can actually do changes on the vessels that they are going on and whatnot. And these problems are big. I mean, for pricing, airlines, you have number of flights, number of commodities, times number of periods, order of magnitude. Same for mining, number of mining blocks, number of years, precedence, and number of processes to consider. And for the Myers-Linerly problems, you have the number of classes of vessels, which are different, number of ports that you're considering, periods, number of commodities, number of lanes that you're considering, and the speed, if you want to discretize everything. And that is fairly big. So for airline problems, you are kind of in the boundary of what we can handle today, and that's why they use it. It's still doable. It's not too bad. And actually, they run these LPs very often. For mining problems, if you try your favorite solver, it will die a horrible death. And for network design problems, if you want to go to the scale of the world, when you are designing the grid for the whole world, it's just no way. But it doesn't mean that people don't do something about those problems. I mean, people try to do something anyways. And there is literature on trying to tackle some of these problems. For the mining resource problems, there's a special algorithm that takes advantage of the particular structure of the problem. Those mining problems, and believe me, I mean, there are links that you can look up, are essentially just network problems with a few side constraints, where few is order 10, 20, 100. And there is a beautiful paper by Dan Binstock and Zuckerberg, which is a cousin of the famous Zuckerberg, that says, never mind trying to solve the full problem. The only important thing is to guess. I mean, because this is an LP, if you have a network plus side constraints, you know that the number of fractional variables is going to be not order, essentially n plus one number of side constraints at most. And the algorithm goes by trying to guess which subset of variables are going to have that same value, and it works beautifully. And that way you can go. But for the linear-linear instances, so this is just an example of how you can model these problems as an MIP. For the small ones, so what is this? This is West Africa, this is the Mediterranean, just looking at the Mediterranean Pacific, world small, there is a world large, and so on and so forth. Number of variables, constraints, and non-zeros, so you go all the way from a few millions all the way to, I don't know, 700. You can go even larger, 1.2 billions non-zero, no problem. Why would you look at these problems? Actually, these problems at the top, the smallest one, you can solve them. And what happens with those problems, and it's very similar to the situation in the mining problem, is that the hard part is solving the LPs. After you solve the LPs, you do a clever rounding heuristic, or if you kind of let even branch and bound go, you'll get solutions within 1% of the LP bound very quickly and very easily. And you want to do that. You want to get the nice solutions. What happens if you try, these are the smallest instances. You see, we went back from 9 million to just 122,000 non-zeros. And in these instances, simplex is just struggling. And these are not particularly big. Number of iterations, 1.8 million, 1.2 million, 3 million, 10 millions, some timeouts here, because I put a time limit of 2 days, essentially. So it's a horrible death. And you may wonder why. And the question, if you start digging into the algorithm, what's happening is Bland's rule, which no one used. Essentially, the what's the word? I lose it. Degeneracy in the simplex pivots. All solvers have heuristics. I mean, when we teach this to the students, if we teach it at all, we say, oh, don't worry, you use Bland rule and you are guaranteed to find the final optimal basis, and that's that. If we ever tell them about this issue. In practice, what solvers do is that they do perturbation. Because, I mean, that's the funny thing with LPs. In theory, if you take an LP randomly, degeneracy will never happen. If you solve all the practical problems, all of them are degenerate. So the trick that the solvers do is that they perturbate the problem a little bit, just randomly, and hope for the best. And that's what happens. So the Grove and all the solvers are tuned for what we've seen in the standard instances, and in this instance, because the network structure is so much bigger, it just dies. No way to get anywhere close where we want. Grove on barrier is much better, much better. You still see this very nice low number of iterations. They're expensive, but very few iterations. But time starts to be an issue, but not only time, actually also memory. Why? Because barrier, I mean, what they are doing is the path following interior primal dual, yada, 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 which essentially take the matrix, the transpose of the matrix, you take the product, and then you do a QR factorization. So the product already fills in. So if you had a sparse matrix, the product may not be sparse, probably it's not sparse. And even worse, when you do the factorization, your memory requirements are blowing up in your face. So that's the big problem in this case. And that's why it dies a miserable death too, because these problems are big. And this is running on 128 threads, 96 gigs of RAM. And actually the 128 threads is not very much useful for barrier, not for the way they are coded today, because there is not a whole lot of opportunity for parallelization. And I'll come back to that later. So at least in this class of problems, all the common wisdom is just not true. These problems are hard because of the size of the problem. So what's the goal? If you had a wish list, what would you hope for? Well, you will hope for a problem that really, I mean, for an algorithm that is really able to solve very, very large LPs. You will want it to be amenable for warm starts because we really want to solve MIPS, not LPs. You also want to exploit parallelism, much heavy than what we do today. You want to solve models consistently, and you want, and this is just my particular viewpoint, that you want to exploit the network structure, just because we know so much more about networks and how to solve them and whatnot. So that's what you will really like. And there is a question. I'll come back to this question. So solve models consistently, and when we solve, what do we mean when we say we solve a problem? Actually, yesterday, Rothberg was talking about that in a webinar of Gurobi. He was complaining heavily about all the hype on PDLP, and I'm going to talk about that a little bit too. So alternative methods, and I'll start talking with PDLP, of course. So what is PDLP? So this was a surprise. This is fairly new, 2021. And this should not work, actually. If you think about it, what they are doing is this. This is a first order method, very simple, where you do an iteration, a first order iterations. The next point is just your dual times the transpose matrix, some parameter there, and you do a projection into the positive cone, and the next dual point, you look at the previous and the current X, iterate, you iterate over A, and you do that update. And the vanilla proof for convergence is just a fixed point theorem. This is well known, and the convergence is 1 over K in theory. And actually the initial experiments that they did with the vanilla set up that you will get from the theory was disappointing. They did quite a number of tricks to make this work. But it has many of the attributes that we would like to have. So this can solve very large LPs. How large? I mean, they can go to a couple of billions non-zeros by doing distributed computing on several machines. So they can do that. It's not clear how amenable or how effective worms are. I mean, you can give the previous iterate and see what happens. But we haven't have time and enough experience to see how effective is going to be the worm starting. As I said, parallelism, it's almost trivial, and I'm going to show you how later on. And it can solve models consistently, and it's not clear how to use network structure. That's the only drawback here, or one of the two drawbacks. But it can do much better than what Gurobi was doing on this set of instances. So Gurobi was dying in the 23 million non-zeros and 2 hour plus. This is also running on the same machine, 128 threads. This is the number of iterations. Those close to the 2-day limit is essentially timeout. But you get, I'm sorry, and here is PDLP with 1% optimality gap, but 10 to the minus 8 feasibility tolerance, which is very tight. So these are very truly feasible solutions with some gap. And it's going a long way. I mean, all the way to 127 million non-zeros. Sure, it takes a while. And if you really want to push the limits, 10 to the minus 6 optimality, it's taking quite some time. I mean, and we did these experiments even for the largest instance. For the largest instances, it took 330 something hours, but still got there, which is quite impressive. But there is room for improvement, clearly. I mean, what PDLP is doing is, you look at the gradient of this first order, it's not looking at any of the structure of the problem. If you have if your gradient is pushing some variable to go up, it will go up, but since it's not looking at the network, it will take at least the depth of the network to propagate that change to be feasible again. So no wonder it's taking so long to converge in terms of number of iterations. So there is a chance that you could speed up this.
By exploiting network structure.
By exploiting network structure, yes. So what PDLP does on MIP, this is the same instances, and it's not as good. But you will see here that there are some instances where PDLP is better, especially on the larger side. And it's not surprising. I mean, this is 16 threads, it's still feasibility 10 to the minus 8, which is probably too tight. I mean, this is what David thinks we should be using. I don't agree. I think that we should be using 10 to the minus 6, but, well, it's his code, so he took the lead on that one. But there is opportunity also on MIP instances. If you think that this is CPU code, Rotberg was saying that you can get a GPU advantage of 10x, so that will go down at least 1 order of magnitude. I will argue that you can do probably a bit better, maybe 2 orders of magnitude, and then it will be competitive even on MIP instances. I mean, the newer GPUs, they have 64 gigs of RAM, which is, you can write the dense matrix for many of these problems completely in the GPU and just iterate. The bluish and the purple. So the one that it's up here and a few down there. So the greens are simplex and the red is barrier. So, I mean, it's still solved quite a bit. Number of iterations, it goes crazy too, but not always. So that's PDLP. And why I started working on these linearly problems is because, well, we had the possibility of collaborating with them and they wanted to solve this very large problem. And because I knew that you could solve, I mean, that for the smallest instances, the periodization plus rounding did the trick. I was hoping to do the same for the larger ones. And PDLP was able to solve this larger piece. And indeed, we were able to get interesting solutions, non-trivial solutions using that trick. But still waiting 303 something hours for just one LP seemed too much to me. And I say, well, why not try something else? And there are more things around. So this is an older paper by Roberto Comenedi. And his idea is to use exponential penalization for LP. And why? Why I was looking at exponential penalizations? Well, because barrier is a penalization method. The drawback of barrier, why, or one of the reasons why you cannot parallelize it, I mean, worm started better, is because you need an interior solution. With exponential penalization, you don't need interior solutions because it's, well, exponential. You can go beyond. And his idea is very simple, essentially. You are penalizing all the constraints with an exponential penalization and a parameter mu right there. And well, he was doing Newton directions, which is in principle not clear how to do it if you don't want to do factorizations of your matrices and some other stuff. And it's like a path following method. It does have a superlinear primal dual convergence. So when you're close enough, the dual variables that are implicit in the algorithm converge exponentially fast to the optimal duals. Does not require interior point. It should be asymptotically like other interior point methods. It's not a self-concordant barrier, which could be a problem. But and there is little direct computational evidence on how well this will work, but it was a possibility. And let me move on. So we had this idea, okay, maybe we can take back this algorithm, use the exponential penalization, but it's not clear how to use the network structure on that algorithm. And talking about this, so Dan said, oh, well, but you should look at these papers, you know, all this packing, covering, exponential penalization literature, which is this. The soft max covering packing with oracles. It's a beautiful literature. Starts in the 90s. There is a bunch of papers, Tardos, Mois, Grigoriadis, Kachijan, and Dan has a book on this. And what's the idea? And I know this looks ugly, but I'm going to show you a little bit simpler form of this. You want to solve kind of a feasibility problem. What's lambda is some maximum value of a set of positive functions. But these functions are defining over a set which is a product set. And each subset, each of bk, is essentially kind of an oracle. And you can decompose the function into sub-functions. So their idea, and there are some extra requirements. The functions should be positive. These have to have an interior point, and there is quite a bit of extra things to require. And in my opinion, although this is more general, what actually they are trying to solve is network problems with some side constraints and with positive side constraints. That's very big for them. You need the matrix A to be positive, and you're trying to push the lambda down so that to find out if you find a feasible solution to the side constraints. That's what essentially they are doing. It's much more than that. But the analysis is hopeful. I mean, if you look at the papers, it took us a while to understand what was going on. In the end, we did. And what they prove is this, essentially that by using the oracles of solving these sub-problems on each sub-network, if you wish, you need this order of magnitudes of oracle calls to get a solution to this kind of feasibility problem. That's what they do. Okay?
Is this something like multiplicative weight update that's happening here? Because the order terms are similar to experts' algorithm.
To which one?
Multiplicative weight update.
There is something like that, yes. And the key idea is that they transform this min-max, that's what lambda is, you're minimizing the maximum value of this set of constraints, into a soft min-max, which is an exponential sum of these ratios and the soft max, and then the oracles is just a Frank-Wolf oracle on the gradient of this regularized maximum function. As I said, analysis is very involved and the setting is very restrictive, but that's what they do. And with Roberto, we sat and said, you know what, we can do a better analysis of this, a simpler analysis, and we can get rid of many of these side constraints. And I'm going to show you what we got. So think on the existence, the feasibility problem. Does an X exist such that your side constraints, in this case now, they are general? AX less than or equal to B, you have a bunch of network constraints, and you have L less than or equal to, a compact domain, okay? That's all I'm requiring. A is whatever you want, and N is an L1. So, of course, that to solve that problem, for that problem to be true, you need to know if there exists such an X such that the network part is feasible. And that's easy. You just run your Oracle mean cost flow and see if you can find anything. And after you do that, you say, oh, well, I can recenter my problem and take this x0 as an initial point. Of course, you have to change right-hand side and all that stuff. But essentially, now you can look at the curve of a problem. It's a slightly simpler thing. And you may hope to get parallelization through the sub networks that you find. And in the case of the big linear problems, you can find 150,000 network components. That part is there. The possibility is there. And what you do is, again, the same trick, but slightly different. So they were using normalization, lam AXI over BI, because they want a right-hand side of 1. And it turns out that you don't need that, at least for most of the analysis to follow. You just take the violation. And you penalize the violations, and minimizing the violation is the same as the soft-max violation. That's all that there is to it. And I'm gonna take even the bounds into the constraints. Okay? So you still have a compact domain, but it's hidden in the lambda mu, in the penalization function, and you keep just the nx equals 0, which is much simpler to handle. And you can get a local upper bound, and well, this is well known. The lambda mu is a very tight approximation of the max violation. And how tight? Well, it depends on the penalization parameter mu. And you can get this local upper bound, the gradient and some term on the matrix, which is easy to compute actually, times mu. So one way to solve this is to solve this approximation of the upper bound, and you can get an algorithm. And the algorithm is kind of a gradient descent with a fixed point. And if you do the math, essentially the only trick is how to handle this part, and how you handle that part, you do a projection. And how you do the projection, and this part is important if you want to use network oracles, you have to normalize with the norm infinity. Because essentially you're saying now that your network has -1 and 1 for all the variables, but that's just network. So you can solve this problem using your network for oracles. So there is hope. And you can do the full analysis, and you can get an iteration bound like that, and an optimality guarantee with parameters mu of that time, of that kind, and the oracles are all mean cost flow like. And you can do more. And you can try or think about accelerated gradient with projecting directly into the curve, which will be not oracle with flow. It will be more expensive. And I didn't want to do this because I said you need an inverse of P, and I was wrong. You don't need an inverse of P. You can do it, and I'll show you how. Anyway. How to go to optimality? And well, what we will say to our students, oh, if you have feasibility, go into optimality, use a log factor. We can do that. Log factor, if you want, 10 to the -6 is what? 20 times. So if you really want to do it, you wish not to do that. But in principle, you could do that and be done. What about something called exact penalization, which for me was new, but for people that do complex analysis like Roberto, it's kind of duh. And actually, Grigoriadis and Kachijan talk about this. And they have, for their special setting, a way to find this exact penalization. And what they're doing, so what is lambda mu? Lambda mu is regularization of the violation. And note that the violation is 0 in the border, but it could go negative. So what they say is, why do I go to interior? I mean, I know that the optimal solution is in the border. Duh. So at the trivial constraint, 0 bigger than or equal to 0, what will happen then? Oh, now your function is 0 in the interior or close to 0. And by adding this thing, what you're doing is tilting it a little bit, so that now the minimum is essentially the optimal LP solution. That's the intuition behind it. Of course, that number in general is the condition number, and it could be bad, but in their setting, that was somewhat helpful, and it only needed to do 2 iterations. Okay, I mean 2 outer iterations of their algorithm. You could do something else. I mean, you could add the constraint Cx, let's to some bound. You can compute bounds because this is a bounded problem. And as you go, you can always compute an implicit bound on the duals of the C vector. And I was wrong. I mean, I'm not wrong. Well, yes and no. So you can compute the bound. And I was hoping, because the theory on the exponential parallelization method says that the duals converge exponentially fast, but there is a caveat there. The caveat is that is when you are close enough. And if you start far away, you're not close enough. So I'm getting ahead of myself. So in principle, this should work. Sometimes it does, not always, okay? But it is true that eventually, by updating this bound, you could get to the just right setting of the C0 and find the optimal solution and do the same thing. So that's the new theory, and I think it's an interesting contribution, because we are taking the old view on the packing covering LPs with exponential parallelization. We get away from all the extra constraints that they had of positivity, yada, yada, yada. Now you have a general matrix that you can use, and you still recover the oracle complexity close enough and all that stuff. So that is already very nice in my opinion. But I want to compute, that's what I like. And I call what we have Rhea, the goddess of the flows. And again, I mean, this is not fair comparison for many reasons. But I limit the iterations to 200. Why 200? Well, because I want to be like an interior point. I don't want to do gradient descent. Gradient descent is too slow. And if you are doing gradient descent, if you are hoping to get to a few iterations, you essentially need Newton. And we can do that. And I'm going to show you how. And what we have up to now, it's not awfully slow. 200 iterations, you can get 10 to the minus 5 relative optimal primal dual solutions, and sometimes very bad, only a little bit than 2 orders of magnitude. But it goes. It can go. It can compute, which is surprising, I will argue. And even in many linear, I mean, MIP instances, you can find optimal solutions doing that wrong trick. Well, not wrong trick, not perfect trick of using your worst bound for the objective and then improving it along the way. You can solve LPs like the PO201 MPS from MIP, all the mark share problems too in 14 iterations. It goes like blazingly fast. I love it. But it's not true that it solves every problem, nowhere close. Another problem where it does very well is 10 to the minus 5, 10 to the minus, actually gets to the optimal solution in 2,000 iterations and whatnot. Mediterranean, 200 iterations, 10 to the minus 5, I mean 7 point something, 10 to the minus 5, and it's not awfully slow. And there are many things I'm doing Newton. I'm going to explain a little bit of those. Those are fairly big problems. So let me tell you what works. I know that this works and helps quite a bit. And these are PDLP tricks. These two is how you do parallelization for larger problems. And it's trivial, essentially. You do a sharding of your matrix. Whenever you want to do A times X, you pack a number of columns by number of non-zeros, such that each set of packets have roughly the same number of non-zeros, and you multiply independently each one of them to your vector X, and there you go. You can compute it in parallel. Same thing with inner products of vectors. You divide it in groups, multiply, add the result, and there you go. And this is easy. The drawback on this parallelization scheme is that it works well for smaller problems. I mean, for bigger problems. For smaller problems, not so well, because all the synchronization, threads, mutex, you pay a price. But for larger problems, which is what I'm looking for, this is great. What also works, and this for me was new, this is so old. I mean, people that do computational linear algebra will look at me and say, duh. But I didn't know. And Roberto told me, oh, because I was discussing with Roberto Cominetti. Well, barrier is so nice, but the memory requirements are square. And he looked at me and said, well, but it shouldn't be. But it is. I know for a fact. The way it's coded, that's what they're doing. He told me that, but they shouldn't be doing that. You can do this. And what is this? This is conjugate gradient. Conjugate gradient is a very old algorithm to solve AX equal B when A is symmetric and positive definite. And the algorithm is very simple. Essentially, you are computing a projection onto a kind of a skew basis and subtracting and going on over and over. If you compute everything in real numbers, the number of iterations to get the optimal solution or the true solution is the number of components in your vector. That's what the theory says. If you are using floating point, this may diverge. You have to be careful. And if you are careful enough and you are stubborn enough, you can get this to work fairly well to get relative errors of 10 to the minus 6 in much less iterations than the number of variables. But much less. It's really incredible. And how do you compute Newton directions using this trick? So in principle, your regularized function lambda mu x, the Hessian, is positive definite. In theory. In floating point, it's not. Because essentially it depends on the curvature, but if the curvature is 10 to the minus 50, that's 0. So you have to be careful. And what you can do and what you should be doing is that, well, let's call H your Hessian and B your gradient in your point. And you look at this form. This matrix now is for sure positive definite. Why I'm also multiplying the gradient with H? Well, because the gradient itself can be computed with some numerical errors. And this is very kind of fickle to numerical errors. By multiplying H times B, I'm ensuring that this is matrix is able to generate that vector. So that's one trick. And the epsilon is to ensure the positive definite. So by doing that, you can compute Newton directions for your favorite function. And you can do this in sparse matrix vector product. Why? Because the Hessian is actually a product of A transpose, and some other vectors in between, but you don't have to compute the product. You only have to compute X times whatever chunk of the matrix is coming. And that's all there is to it. So you never ever compute a dense matrix, never ever compute a factorization, so your memory requirements stay very low. And you can do the same for solving nx equal b. You can use the same for computing actual exact decompositions of your objective vector to get better duals. You can even do the projection, actually not using the network flow, but using conjugate gradient. And there is evidence that if you are using conjugate gradient on matrices that are networked, the method is even more stable and faster. And I've seen it being much better. And again, all this you can still do by these simple tricks of sparse matrix vector multiplication and vector multiplication. Other stuff that are important if you want this to work. Pre-processing. I mean, everybody talks about it, but really, I mean, you have to be doing linear programming, bound strengthening, and dual LP pre-processing for this to work. It makes a big difference. Scaling and iterative refinement, zooming in. What I mean about this. So These are exponentials, and exponentials are tricky functions, and floating points are far away from being real numbers. So if you have big right-hand sides and you are moving a little bit here and there, your floating point resolution is just bad. But if you take out your current iterate, or you are close to being 0 in the iterate, all the numerics improve quite a bit. And also, if your epsilons are getting smaller and smaller and smaller, well, you can just zoom in. And working in the zoom in space, again, makes all the numerics much better. And the other trick, if you want to play with this stuff, is that when you are evaluating these functions, the exponential of a big number is going to blow up in your face. But because you are taking mu, log, exponential, whatever, you can factor out the maximum. And if you factor out the maximum, you only are taking exponential of numbers of 0 or less, or, I mean, you know, you're bounding stuff. And even better in the gradient, when you do compute the gradient, because you still get this term in the denominator, that common factor gets out. So that helps with the numerics quite a bit. The bad, yes, no? Vanilla dual convergence is slow. I clearly not understanding everything. We've been talking, maybe we should try a primal dual version, and not just taking the primal. Newton directions for this function can be orthogonal, and I think what is biting us is the self-concordancy of the part that we're looking at. I don't know. How to choose mu, honestly, you just have some rules, and sometimes they work, sometimes they don't. And that's bad, because you don't want an algorithm like that. You want a parameter-less algorithm. And this is, and I cannot stress this enough, this is very important. This is going back to what do we mean when we say that we solve a problem. And Robert was also complaining about this, and rightly so. So we've been used to what the solvers give us, which is fixed precision, 10 to the minus 6 for, that's the standard, primal dual tolerances. Internally, they do something else, and if they cannot meet those precisions, they will lie to you, and if you're not careful, you're going to buy their result. But in general, they are very good at getting that kind of precision. In this world, for PDLP, for what we're doing, scaling is key, and what norm you're choosing and what's the ending criteria is important, because, I mean, for example, a 10 to the minus 4 tolerance for relative tolerance for some famous LPs like the PDS, the PDS 100, means that you are violating some constraint by the order of tens of units, which is fairly big. So how small it must be, it's kind of an open question, and for the people that is doing the algorithm, it is very important to keep in mind. And that's all I have for today. Thank you for your time.